Welcome to lecture 21 of Power System Protection course. So in the last lecture, that is lecture number 20, we discussed about the transformer protection. In fact, we started the transformer protection in lecture 19, and in lecture 20 we discussed more about the transformer protection. We discussed about how in a transformer, in a delta state transformer or star delta transformer, in fact what should be the connection of CTs, how the CTs can be connected, and what should be the CT ratio, how we can decide the CT ratio. So all those things we discussed, and then we discussed how for an external fault, how this kind of arrangement will not respond if we are considering an ideal situation, ideal CT and other things. Similarly, also we have seen how it will operate if there is an internal fault. Internal fault happens in case of transformer that lies inside the zone of protection. So today also we will continue with transformer protection, and in this lecture particularly we will see with an example illustrating how we can design a differential protection scheme for a transformer, and then we will talk about different other faults, other abnormal conditions, like if there is inrush current, how the protection scheme will behave and what modification we need to do, and also we will see about the high resistance earth fault, how it can be protected, how a protection scheme can be developed for protecting against the high resistance fault, because generally for a high resistance fault, because the current value is low, so therefore the normal relay which is there in case of differential protection, now normal overcurrent relay, it doesn't respond because it doesn't become sensitive to that, because the magnitude of the current is low. And then gradually we will see other faults in next class. Okay, let us start with lecture number 20. So before starting, let us just see what we discussed in the last class, in the last slide. So we considered a delta star transformer. In fact, in the delta star transformer, we considered a fault which is internal fault, that is from phase C to phase C to ground. We can see here this is the fault, and for the internal fault we have considered two cases. One is your bolted fault case, other one is your arcing fault. For bolted fault case, here as soon as it will become shorted, here this IC will become 0. So as this IC will become 0, therefore the spill current will become I capital C. Already we have seen this, right? Already we have seen how it will become IC, because this here IC will become 0, here you can say here IC will become 0, therefore your here IB, in fact IC is 0 here, okay, and here IC minus IB, and here it will be IB will flow in fact, but IC will be 0, therefore here capital IC will flow, and here similarly also minus IC will flow. Okay, so already we have seen this, that here we can see here IC minus IB is flowing, and in this line if we will see your IC minus IB will flow, but IC small c will become 0. So therefore minus S, and therefore I capital C will flow in the spill path. Similarly, here in this branch also I capital A minus I capital C will flow in the left side, and in the right side it will be IA minus IC, I small a minus I small c, and your, because I small c is 0 here, right. So, this is 0, and therefore IA will flow here only, and minus IC will flow in the spill path. So, therefore, we have now two currents in the two phases in the spill path, and that will cause in fact the overcurrent relay to trip or to give the trip signal to the circuit breaker. So, next we will see the arcing fault. So, in arcing fault also we have seen that because some amount of current will flow here. So, here therefore, the current will flow IC minus I capital C minus I small c, and where I capital C is not equal to I small c. In fact, I capital C is greater than I small c. So, therefore, it will be IC minus I capital C minus IC, and in this spill path in this phase it will be minus of I capital C minus I small c. Okay. So, already we have discussed these things, and let us consider now the numerical problem which we through which we can illustrate. So, what is the problem statement? The problem statement is, so we have a 45 MVA transformer and the voltage rating is given 11 kV, 66 kV, and the transformer is a star delta transformer, right. For star delta transformer we know that for star side the relation between the line voltage and the phase voltage is √3 VPH, and similarly for delta side your VL equal to VPH, that is line voltage is equal to the phase voltage in case of delta side, right. Now, if we will find the transformation ratio for this case, it will be for VPH it will be VL by √3, right. So, now you can find the ratio will be, because these are the line voltages. So, your transformer ratio will be how much? It will be 11 by √3, because the primary side is star connected, divided by 66. So, it will be 1 by 6 √3. Okay. So, let us design the percentage differential scheme for this kind of arrangement, and what is the minimum recommended percentage bias we need, and we will consider 5 ampere relays in the differential scheme. That means the secondary side relay current will be 5 ampere. Okay. Relay current will be 5 ampere. Okay. So, now let us design, let me erase it. So, let us consider now. So, here we will talk about the different steps of design, and this will be for the both side of the design. First we will do for simultaneously we will do for 11 kV, that is star side, and then we will do 66 kV delta side. Let us first find the full load current. So, your full load current will be, so these are the steps, let us note down the steps. Step 1 is to find the full load line current, then to find the overload condition of 25% as the primary current, because IFL in order to set the relay setting. So, we need this kind of overloading condition, right. Then we will find the CT ratios considering 5 ampere relay, right. That means the 5 ampere current is flowing in the secondary side of the CT. Then fourth step is we have to find the CT secondary current, right. So, let us find, then we will go for next steps. So, now if we will find the primary side or 11 kV side star side line current, it will be 45 MVA, 45 into 10 to the power 6 by root 3 into 11 kV, because 11 kV is your line voltage. So, therefore, root 3 into 11 kV and your current value is 2361.88 ampere. Similarly, if we will find 66 kV delta side current, we will just divide 45 MVA by root 3 into 66 into 10 to the power 3. So, it will become 393.64 ampere. Okay. So, now we can see just to find the overloading condition, under overloading condition of 25%, how much current will flow. So, just by multiplying 1.25 in the current, full load current, we will find overloading of 25%, that will become 2952.35 ampere. And similarly, for secondary side, for 66 kV side, it will become 492.05 ampere. Okay. So, now the question is to find CT ratio. Already we know that previously I told this, when we assume the CT ratio at the primary side, we can find the CT ratio at the secondary side. If we will say that T is the transformer ratio and N is the CT ratio at primary side, then in the secondary side what will be the CT ratio? So, secondary side CT ratio will be it will be T into N. Already we have derived this in the last class, right. So, it will be Tn, just remember this. And now we will go ahead with this. So, let us see what is how we will decide the CT ratio. We can see here in the 11 kV side. So, the CT ratio is assumed as 3000 is to 5, because the current is around 2952. So, therefore, it is assumed 3000 is to 5, it is standard CT ratio, right, and the CT ratio became 600. That means your N equal to 600, right. Okay. Now, your secondary side CT ratio should be NT, right. So, T is the transformer ratio and N is your CT ratio of the primary side. So, primary side CT ratio is known 600 and transformer ratio is known, that is 1 by 6 root 3, right. So, if we will multiply these two things, it will come an irrational number, because 600 into 1 by 6 root 3, it will become 100 by root 3, right. It will become 100 by root 3. So, this 100 by root 3 is in fact irrational. It is very difficult to get an exact turns ratio, and in standard CTs manufacturer never make such CTs with ratio of 100 is to root 3. So, therefore, what happened, in order to make it standard match with the standard availability of the CT, standard CT availability. So, we considered 100 as the CT ratio, and therefore, the CT in fact primary side turns will be 500 and 500 is to 5 and your CT ratio will be 100. So, let us assume as 100, right. 1 by root 3 we cannot make, it is very difficult in case of CT designing, right. So, now we can adjust this 1 by root 3 later on by using an interposing transformer, we call it interposing transformer. So, rest 1 by root 3 will be adjusted using the interposing transformer, which is an auto transformer in fact, okay. And it is easily we can do this using this because it is auto transformer and it is possible to do to adjustment, right. So, now let us see next step is your CT secondary currents. Now, just dividing the CT ratios, we can find the CT secondary current. Your CT secondary current will become 2361.88, okay. So, this is your current, full load current by 600. So, under full load condition, if we will calculate the CT secondary current, it will become around 3.936, okay. So, now this is your CT secondary current, and CT secondary current for the secondary side, for 66 kV side, and that is delta side, if we will divide 393 this 393.64 by 100, we will find 3.936 ampere. So, it seems both are equal, but the current flowing in the pilot wire will be different. It is the current flowing in the secondary winding of the CT, but if we will calculate the current flowing in the pilot wire, it will be different. So, let us see the current in the pilot wire, how much it will be. So, then step 5 is your pilot wire current. How we will find, because this is a star side, primary side. So, your CT will be connected in the delta fashion, right. So, delta fashion means the current in the pilot wire will be root 3 times, that will become current in the pilot wire in the delta side will be root 3 times the current in the winding, that is 3.936. So, it will become 6.816 ampere, right. Similarly, if we will find the current in the star side, because the phase current and the line current will be same. So, therefore, the current in the pilot wire will be 3.936. So, there is a huge mismatch between these two currents in the pilot wire, right, which is coming from the primary side and which is going into the secondary side. They are huge mismatch. So, therefore, in order to balance this mismatch, this mismatch in fact because of the irrational CT ratio we found, and we assumed the CT ratio as 100 instead of 100 is to root 3, right. So, we calculated the secondary side CT ratio as 100 is to 100 by root 3, but we took it as 100 in fact, because it is coming an irrational number, we cannot design such CT 100 by root 3 ratio with 100 by root 3 ratio, right. So, therefore, here we adjust this current, make the current balance using the interposing CT, right. So, therefore, the turns ratio of the interposing CT will be how much? It will be 6.817 divided by, so both the current will be divided 3.936 is to 1. So, it will be 1.731 is to 1, that means root 3 is to 1, right. Okay. So, now current after the interposing CT. So, after installing the CT, what is the current? That current will become 6.817 by 1.731. So, it will become 3.938 and this current is 3.936. So, now the currents in the pilot wire from both sides, they are almost equal and there will be no spill current, right, under normal load condition. Now, we can see in the figure the conditions. Here we can see your transformer rating was considered 45 MVA and it is 11 kV, 66 kV star delta transformer, right. And the CT ratio, first we assumed in the primary side as 3000 is to 5, considering 3000 is to 5, considering the overloading condition of 25%. And then here the CT ratio is found to be 500 is to 5, because 5 ampere we have assumed that 5 ampere relay is being used. So, secondary current of the CT must be 5 ampere. So therefore, in order to make this CT ratio 100, it is become 500 by 5, 500 is to 5. Now if we will see under normal load condition, primary side your current is 23, line current will be 2361.88 ampere, and your secondary current is 393.64 ampere, and in the secondary side of the CT the current will be here how much, it will be 6.817 ampere in the pilot, in the secondary side of the CT, right, and in the secondary side of the CT of the in the delta side will be 3.936, and which in fact flowing in the pilot wire in the secondary side, in the high volt in the delta side, right. So in the star side in fact it is a mismatch, therefore we used here interposing transformer, right. So you can see here the interposing transformer is placed, in fact the secondary side of the CT current is 3.936, but the pilot wire current becomes 6.817, because already we have seen it will be root 3 times 3.936. So this is your pilot wire current, okay, at the primary side, pilot wire current, primary side, and in order to make balance of this current, both from primary side and secondary side, so the interposing transformer is used here. We are having the ratio of 1.731 is to 1. So now your current after the interposing transformer will become 3.938 ampere, right. So now this is from here, from primary side, from star side it is coming 3.938 ampere, and it is in fact going to the delta side 3.936 ampere, right. So therefore your current in the pilot wire they are balanced, and your spill current will become almost 0, right, okay. So this is how we design the percentage differential relay. So then this percentage biasing can be adjusted based on the number of turns in the restraining coil and the operating coil. Okay, so now this is all about your transformer protection scheme. We have not completed it, but this is all about the transformer protection scheme, differential protection scheme, in order to protect the internal faults which happens in the terminals of the transformer, right. It is not inside in fact not inside the transformer, because inside the transformer there is no such fault happens like line to line, line to ground, line to triple line faults, right. So this is in fact happens in the terminal of the transformer. So now let us see the inverse phenomena in the transformer, then how this inverse phenomena can be distinguished from the fault current, and in fact how the protection scheme can be modified in order to distinguish the inverse phenomena, and it will give the trip signal to the circuit breaker. We will see in this slide. So let the voltage be represented. So let us consider a transformer which is operating under under no load condition, unloading condition, right. So let the voltage be represented as V equal to Vm sin omega t plus theta, okay. So now if we will write the equation for the voltage, in fact if we will write the voltage, this is the applied voltage. In fact for an ideal transformer the applied voltage is equal to the induced EMF. So I can write it as N d phi by dt is equal to V, okay. So therefore from this equation I can write N d phi by dt will be equal to Vm sin omega t plus theta, which is nothing but the applied voltage. Now if we will find the expression for phi from this equation, then just by integrating I will find this equation. If I will integrate, I will find phi equal to Vm by n sine of omega t plus theta dt integration, right. So, that will give me minus Vm n omega cos omega t plus theta plus k. K is your integration constant, right. Okay. So, k is the integration constant. Now, the value of k can be found out from the initial conditions. So, let us consider the initial condition when t equal to 0, phi equal to phi r, that is the residual flux in the core, because always some residual flux is there in the core if the transformer is in use, and suddenly the transformer is under unloaded condition and the voltage is connected in the primary side, supply is connected in the primary side, then under that condition your phi will be equal to phi r, that is the residual flux in the core. So, substituting this initial condition, if we will substitute t equal to 0 and phi equal to phi r, we will find that phi r equal to this Vm by minus of Vm by n omega cos theta plus k, and from this equation I can find k. So, k will be equal to phi r plus Vm n omega cos of theta. Now, in the place of k, if I can write this expression, so I will write phi equal to, the expression of phi will be written in terms of phi r, that will be equal to phi r plus Vm by n omega cos theta minus Vm by n omega cos omega t plus theta. So, this is your expression for flux in the transformer under unloaded condition. So, thus the flux in the transformer is a function of the following three factors. What are the three factors? First is your residual flux phi r, and second one is your instant of switching q. So, that in fact decides theta. It is not q, in fact it is theta, right. Instant of switching theta. Then the magnetic properties of the core, that is the amount of magnetizing current required to produce a given amount of flux. So, now we can see that for theta equal to 0 and phi r equal to phi m, if we will consider theta equal to 0, that switching instant when theta is equal to 0, and phi r is equal to phi m, the flux attains an amplitude of 3 phi m at omega t equal to pi radians. Okay, so it, in fact, if we will go to the last equation, in this equation if we will substitute phi r equal to phi m, and your theta equal to 0 and omega t equal to pi. Okay. So, what will happen then? It will become 3 pi m, 3 phi m, right. Okay, that is what it is mentioned here. It will become 3 phi m. Okay. So, the transformer primary draws a very large magnetizing current with a peaky non-sinusoidal waveform. So, under this condition, as the flux becomes very high, in order to provide that flux, in fact your magnetizing current will be very high. So, therefore, the transformer draws a very large magnetizing current. So, why it is so? You can see here large magnetizing current, and it is in fact not sinusoidal, it is peaky in nature, very much high value, high peak, right. So, here we can see we are applying the voltage Vm sin omega t, and your inverse current will depend upon the flux here, flux in the core. So, when the flux is phi r phi m cos theta minus phi m cos omega t plus theta, and under the condition when phi equal to, when phi r equal to, when phi r equal to phi m and your phi equal to, your theta equal to 0 and omega t equal to phi, then under this condition this phi will become 3 phi m, which is very high value in fact, and therefore in order to provide this high flux value, so your magnetizing current will become very high, right. You can see from this figure how it becomes very high, right. So this is the normal operating condition. Generally the normal operating condition for the power transformer is at the knee point, right. So we call this as knee point, okay. So and beyond the knee point, any more flux we need, right. So your magnetizing current will become very high. This is your magnetization curve, right, because beyond the knee point your core gets saturated, so the magnetizing current will become very high. So therefore here at 2 bm even the magnetizing current is very high, around 8 IO, right. IO is the normal magnetizing current. So around 8 IO it becomes. Under 3 bm it will become more higher, right. So therefore in order to provide this flux, your magnetizing current becomes, suddenly it rises and again suddenly drops within the time period of t by 2, right. Therefore it becomes very peak. So it is peak in nature, and the magnitude is very high, right. So how to then distinguish this current from your original current, original magnetizing or original fault current. So generally the fault current is sinusoidal in nature, and this magnetizing current is not sinusoidal. So we can understand from this that as it is not sinusoidal, so the harmonic content in the inrush current is very high. So therefore during the inrush current, the harmonic content in the current is very high as compared to the fault current. So therefore this is how you really can distinguish from inrush current to the fault current. So when if some arrangement can be made in the relay so that it can distinguish the harmonic content, then it can easily distinguish between the inrush current and the magnetizing current, right. So let us see what kind of change we can do in the percentage differential relay scheme, so that your harmonics in the inrush current will be identified, and so your relay can identify that it's the inrush current, it's not the fault current, so therefore it will not trip, it will not maloperate during that condition. So therefore along with the percentage differential relay, the harmonic restraint is developed. What is this harmonic restraint? This harmonic restraint in fact is nothing but, if we can develop more restraining torque by using the harmonic content that is inside the inrush current. Somehow if you can design a system so that your restraining torque will be more when the harmonic content is more, when the restraining torque is less when the harmonic content is less. So for inrush current, when the harmonic content is more, the restraining torque will be more and it will oppose the operating torque, and therefore there will be no tripping of the relay. Okay, now we can see the scheme here, right. So in fact in the CT secondary currents we have I1 and I2. So these are the CT secondary currents, both the side, primary side and secondary side of the main transformer, and in the spill current is I1 minus I2, we know this, and the current flowing as circulating current is I1 plus I2 by 2. Okay. Now if we can design some kind of filter in the spill path, right, and if that filter can segregate these two components, that can segregate the fundamental component and all harmonic components, okay. So then what will happen, the fundamental component will pass through the spill coil, pass through the operating coil in order to provide the operating torque, and your harmonic content will fade to the restraining coil. So, to the restraining coil we have the circulating current is being flown, that is I1 plus I2 by 2, which is having fundamental plus all harmonic content, right. Again in this we add all harmonic content, right. So, then by combining these two, if we will send to the restraining coil, your restraining torque in fact will become more, right, as it is previously. So, as it is previously, it will become now more and it will oppose the operating torque. So, therefore, the relay will not maloperate under this condition, this inverse phenomena condition. Okay. So, this is how we can design a percentage differential relay with harmonic restraint. That means, the harmonic content of the current is used to develop more restraining torque in order to avoid the maloperation of the relay. Okay. So, now this is the scheme by which we can in fact implement this kind of relay. So, here we can see that CTs are both the side of the transformer, this is your transformer, and now we can see here we have operating, this is your spill path, sorry, this is your spill path, right, spill path, and this is your circulating path. Okay, this is your circulating path, and in the spill path the current is I1 minus I2, and your circulating path the current is I1 plus I2 by 2. Okay. So, now we can see here that here if we can do some arrangement, right. So, this arrangement in fact helps us. Here this is the filter circuit which in fact passes only the fundamental component, right. Okay. So, which is being fed to the operating coil. Now, you can see the fundamental, it passes this filter in fact only passes the fundamental component, blocks the harmonic content. So, therefore, the fundamental component is being fed to the operating coil through a rectifier, right. Now, similarly, this is a filter which in fact blocks only the fundamental component, right. You can see this filter in fact only blocks the fundamental component, and it passes the because it is a parallel circuit of capacitance and inductance. So, therefore, as the current frequency becomes more, so your path will become your impedance path will become less. So, it passes only the harmonic content and blocks the fundamental component. So, therefore, this 2 you can say here the 2 is added here, right, 0 and 2. Now, it is fed to a rectifier circuit and it is combinedly fed to the restraining circuit along with the spill current. Here the spill current is where we are receiving the spill current from 3 and 4, right, and this is fed here in this circuit. So, this is your this is your circulating current, sorry, this is your circulating current, which is in fact combination of both fundamental plus harmonic circulating current, right, and here this is the all harmonic content of the spill current which is 0 and 2 marked, right. So, 0 and 2 is fed here only the harmonic content from the spill current, and it is fed to the restraining coil, right. So, this is fed to the operating coil. So, only the fundamental component of the spill current is fed to the operating coil, and in the restraining coil the circulating current which is consisting of fundamental plus harmonic current plus all harmonic spill current is fed along with the circulating current to the restraining coil. So, therefore, now the torque developed in the restraining coil will be more as compared to under normal condition as compared to normal condition. So, therefore, it will restrain when there is inverse phenomena in the transformer. Okay. So this is all about your inrush, how the differential scheme can distinguish between inrush phenomena and the fault condition. So now we will see the restricted earth fault protection for high resistance ground faults. Let us first understand what is this high resistance ground faults, and then we will talk about the restricted earth fault, why it is called restricted earth fault protection. Okay, so high resistance ground fault means sometime your fault happens in core, in winding to core, right? The fault happens from winding to core, like here winding to core fault. So here we can see, here we have a delta star transformer and the fault suppose happen in the winding, and in fact it is shorted to core. So the winding insulation is deteriorated and the winding is shorted to the core somehow. So that is called winding core fault. So in fact this winding to core fault is high resistive in nature. Why it is high resistive? Highly resistive in nature, because we know the core is laminated, and inside the lamination we have lot of ingredients, sandwich, those things are the varnish, paper, all these things in order to reduce the eddy current in the core. So therefore when the core is being earthed, core is being sorted with the winding, the core in fact provides the high resistive path, right? So therefore it is called high resistance ground fault. It is a ground fault but with high resistance. So as the high resistance ground fault happens, the current value, the fault current in fact under this condition is highly reduced. It is not very much appreciable, and therefore your relay doesn't sense this kind of fault, doesn't sense. So this kind of fault, high resistive fault, is never sensed by the relay. So then for this condition, how to do? There is another arrangement of overcurrent relay is made, which is in fact helps us to with an sensitive overcurrent relay, which in fact very easily detects this high resistive ground faults, and it is designed in such a way that the protection reach, the reach of the protection scheme should be only to the delta side, not to the star side and not to the opposite side, right? So only it will protect this much of range, right? Okay, the reach of the restricted earth fault protection is this. So we can test here. Suppose we have under normal operating condition how it will operate, and under fault condition how will it. So under normal operating condition, obviously when the current will flow here, right, the currents are flowing in this direction in each phase, and therefore your CT current will be out from the dotted terminal, right, and therefore here it will be the sum of the currents IA plus IB plus IC, right. So this will be in fact 0 all the time, whether it is a balanced condition or unbalanced condition, it doesn't matter, because this is a delta side, delta winding, right. So therefore your sum of the current IA plus IB plus IC will be always equal to 0, right. So therefore let us consider another fault which is happening in the star side. So even as the fault happens in the star side, so what happens? Your current in the delta side will become unbalanced. Even if it becomes unbalanced, your IA plus IB plus IC will become 0, right. So therefore your overcurrent relay will not trip. But under the condition when the fault happens here in the winding to core fault in the delta side, then what happens? Then this current, in fact whatever current is flowing here in the delta side, So now this current will become less than this current, right? Sometime it becomes 0 if it is bolted fault, right? So because it is high resistive fault, some current will flow, but suppose let us say this current is IAB and this is IAB dash. So your IAB dash will be less than IAB, right? So now when this IAB dash current will be flowing here, in fact we can say arrow marks in this direction. So IAB, so I can say IAB is less than IAB dash, okay, sorry, IAB dash, okay. So now the current here will be now become unbalanced in such a way that your IA plus IB plus IC will not be equal to 0, because some current is flowing here in the ground, right, to the core. So therefore here your IA plus IB plus IC will not be equal to 0. So therefore it has some magnitude, and your overcurrent relay will sense that magnitude, and the relay will give the trip signal to the circuit breaker. So now this arrangement is for the high resistance ground fault protection, which is restricted to the delta side, right? Therefore it is called restricted earth fault protection, right? So now let us consider the star side. So for star side, what will happen? Similar arrangement will make, which will only operate during the high resistance fault in the star side only, that is winding to core fault, not for other faults, right? Even the fault happens in the delta side, it should not respond, right? Similarly, we can see here we have 4 cities, they are connected, right, together. 3 cities in the 3 phases, and 1 more city is connected in the neutral wire, which is connected to the ground, right? So obviously if we will do the under normal load condition, if we will do the analysis, so then if your load, let us say load is unbalanced, right? So your city currents will be IA, IB and IC. As the current is unbalanced here, load current, so there will be some neutral current, right? So therefore the current flowing in the relay circuit will be IA plus IB plus IC plus IN, which is nothing but equal to 0, right? If your currents are flowing through going away, then your neutral current will be in this direction, right? And hence your CT neutral current will be here, right? Okay. So therefore your IA plus IB plus IC plus IN will be 0 under the normal load condition. Whether the load is balanced or unbalanced, it doesn't matter, right? Now if we will see the fault at delta side, so if the fault happens at the delta side, your current reflected in the star side will become unbalanced, but still your IA plus IB plus IC plus IN will become equal to 0. But if your fault happens in the star side from winding to core, then what happens? Your current magnitude here will change, and your current magnitude IB will change. It will become in fact IB dash, and which is become unbalanced, and therefore because IN is IA plus IN equal to IA plus IB plus IC, and as the magnitude of IB changed, therefore IA plus IB plus IC plus IN will not become equal to 0 when the fault is in the star side from winding to core, right? So therefore your relay will respond to some current, some magnitude of current, and therefore it will give a trip signal to the circuit breaker. So this is how your high resistance ground faults can be protected, and these protection schemes are known as restricted earth fault protection scheme, because they are quite restricted to a particular side of the winding, right, whether it is primary side or secondary side. Okay. So, based on the arrangement, it is therefore it is called restricted earth fault protection. Okay. So, today we will stop here, and next class we will talk more about the transformer protection schemes. There are many other kinds of faults, incipient faults, then we will see the interturn faults, then we will cover all the transformer protection. Okay. So, thank you very much for your kind attention.